Good afternoon, ladies and gentlemen, and welcome to your final presentation of the day. Today I'm going to speak a little bit about my PhD thesis, which is Superior Structural Design through Automated Topology Optimization and Advanced Manufacturing. I'll spend a little bit of time explaining those terms later on. So to start with, just a little bit of background on myself and how I've got to where I am now. I started my career in IT, doing computational programming some 12 years ago. Upon completing that course of studies, that course of work, I decided that I wanted a new challenge. I went to the University of Leeds to do an undergraduate degree in mechanical engineering, specialising in aeronautical engineering. From there, I went on to BAE Systems graduate training scheme. I spent a year doing submarine engineering and design for nuclear projects. While the work was interesting, I didn't find it particularly challenging compared to my university studies. I wanted something a bit more cutting edge, a bit more research. And so I undertook a KTP, a knowledge transfer partnership, in association with the Technology Strategy Board. That linked to University of Leeds, to EADS Innovation Works, doing research in additive manufacturing and topology optimization. During my time there, I started a part-time PhD here at the university. In 2013, I completed the KTP and moved full-time into working for EADS Innovation Works, looking at concepts for advanced manufacturing and structural optimization. So today I'll break down the presentation into 7 key areas. We'll be looking at introduction and general context in terms of the aerospace industry. We'll be looking at topology optimization and advanced manufacturing and explaining those terms in a little bit more detail, explaining how my research, the context of my research, fits into those 2 areas and expands upon it. We'll be looking at why it ends up with a superior design, why is the design superior. We'll also be looking at successes in public engagement, and then we'll be doing some concluding statements. So, my apologies if you don't like aircraft. This presentation is rather full of them, because that's the nature of my work. But so is the skies around us. Currently, in-service commercial aircraft, there are almost 32,000 commercial aircraft in operation around the world on a daily basis. The industry believes that there will be a requirement for another 33,500 aircraft by the year 2030. Now, these are new aircraft. These aren't replacement aircraft. These are additions to the fleets. So almost doubling the aircraft capacity. In addition, there will be 10,000 business jets sold over that period, which is quite a lot. The design time for a new aircraft is 15 to 20 years. So really, you have to start designing them now for them to be ready for service in that time. In addition, the aerospace industry has set itself some rather ambitious targets. They want to actually cut CO2 emissions by 50% by the year 2020. Now, aerospace emissions are currently 2% of global output, so they want to reduce that to 1% while having almost a doubling of air passenger transport. Now, to do that, we all know that if you want to get a little bit faster, you lose a little bit of weight, and the same is true of an aircraft. In fact, more so. 100 kilograms of mass reduction on an aircraft is 1.3 tons of CO2 saved over the life of the aircraft. Now, that 100 kilograms equates to $2.5 million worth of fuel over the lifetime of that aircraft. So for every total passenger weight you save $2.5 million. So why can't we just keep doing what we're doing? Why can't we just iterate a little further? Well, the Boeing 707, the first of the archetypal aircraft, isn't largely different to the A350 that was commissioned in the last couple of months. The design is an evolution, an iterative improvement from the initial start point to where we are now. The reason for that predominantly is safety. Safety is the main driving criteria of the aerospace industry. Not cost, not performance, safety. You need to be assured that when you get on that aircraft, you're going to get off it at the other side, and the industry survives on that principle. The problem with this, designing from a single point, actually for a common fuselage design, 2 wings, common fuselage, conventional tail, is that all the tools and techniques over the past 60 years have been driven towards that particular configuration arrangement. And as a result, we can't go any further. We're actually approaching a point, a pinnacle of design for this configuration that can't be improved upon. What you need is revolution, not evolution. We need a step change in design and manufacture in order to realize those emission savings. The problem is, to design and manufacture these new parts, we actually need new tools. The aerospace industry is a highly innovative industry. Unfortunately, we have substantial constraints in terms of regulation and safety constraints, which drive us towards the middle ground a lot of the time. What we need to do is actually provide the stability and provide the the tools and techniques necessary in order to create the next generation of platform. So what we need from this is a new series of tools and techniques that will allow us to safely design and manufacture the next generation of civil aircraft. So those new tools and techniques, one of those is topology optimization. Now, topology optimization is basically an advanced form of structural analysis. By structural analysis, I mean analyzing any structure that you see or use: a bridge, a chair, a car, an aircraft. It's built upon the principles of finite element analysis. For anybody that doesn't understand finite element analysis, think of the structure that you just had in your mind when I was talking, and think of assembling that same structure from Lego bricks. Each of those bricks is connected to the next brick. All of those bricks together make a structure. You put a load on the top of the structure, all of those bricks transmit that load to the bottom of the structure. The same is true for finite element analysis, except it's done computationally. The structure, the CAD model, is discretized into an individual domain, and those domains, those bricks, are connected via equations, and that solution to that problem allows you to define whether or not the structure is fit for purpose. Topology optimization works in a similar way, but it builds upon the principles. What it does is it analyzes that structure and determines whether or not those elements, those bricks, are actually important to the structural domain, and if they're not, it removes them. Therefore, you lose mass, you lose weight, you end up with a more efficient structure. So this allows for the analysis of complex designs, something that you can't in your mind's eye design. If you have multiple complex loads, it's very difficult to design for that case in an efficient structure, so you over-engineer it. We're trying to pull it back to make it a lightweight, optimized structure. The problem with these designs is that they're not readily manufacturable. Most topology optimization outputs are incredibly complex, and as such, they aren't suited to common manufacturing techniques. However, advanced manufacturing techniques may provide the solution. One of them, additive manufacturing, or what most people know of as 3D printing, is one such technology. But when I'm talking about 3D printing, I'm not talking about plastics, I'm talking about metals, I'm talking about titanium. What we have here are two 3D printed titanium parts. So these parts have been produced using a process called electron beam melting. They're 100% dense, they're structurally sound, and they will both achieve flight on a commercial platform in the future. I'll just pass those around to the audience, if you don't mind. So these metallic processes are incredibly complex. They use massive temperatures, 1700 to 2100 degrees centigrade. They cool in milliseconds from that temperature, and you build up these structures layer by layer to create complex parts with no waste and very few constraints for manufacturing. They're very, very suited to complex geometry because large structures do not print well. Small structures print perfectly, complex structures even more so. Problematically though, the orientation, the way in which the part is built, can affect the microstructure, the material microstructure of the as-built part. So it sounds like the tools are already there, so what's our research about? What are we doing with this? Well, there are problems with topology optimization. The amount of mass you save is related to the size of the structure being analyzed. Unfortunately, the design, the analysis of that structure isn't related to its size. It takes almost as long to optimize a small component as it does a large one, but obviously you only save a few hundred grams as opposed to a few hundred kilograms. We need to find a way to address that balance. Additive manufacturing, incredibly complex in terms of its orientation, surface finish, performance. We're looking at all of those particular aspects and defining an optimization program that allows us to analyze that structure. Finally, we need to implement these solutions in a manner that is acceptable to the aerospace industry. You can't go all in and apply all of them at the same time. They need to be done incrementally so that the database is built up and it allows those parts to go into service. So what we want to do is take the benefits of additive manufacturing, the benefits of structural optimization, and then apply some process automation into the center, which will allow us to generate a process which can optimize components, complex components, in such a way that they can be implemented on a commercial platform within the next 10 years. So this is one case study, which is actually going around the hall at the moment. It's a business jet door hinge. At the moment, it's a steel design made of two parts and then welded together, 1.6 kilograms in weight. Using the techniques that we've developed so far, non-automated, manually applied at the moment, this results in a design that looks like what you can see. Total mass, 0.71 kilograms, less than about 60% reduction in mass, while a substantial reduction in stress. So why is our design superior? Well, by the time the tools are implemented, you're looking at a 90% reduction in commercial design time compared to what is currently available. So you're talking about going from 6 months with that hinge to 2 weeks ready for use. We also believe that by implementing the optimization process at the very beginning, that we can actually provide a substantial reduction in the waste of the additive manufacturing process, which is already quite low. In total, the number of aircraft programs, the number of small parts per aircraft, we believe that 150,000 tons of CO2 can be saved over the next 20 years. Most of what I research at the moment at Airbus I can't really talk about, but there's 5% of it that I actually can. These are the projects that I sponsor myself, projects with universities. So over the past year and a half, we've engaged 56 different students at 3 universities in multiple level 4 projects, master's projects. One of them is this, a 3D printed, topology optimized, aerodynamically optimized, manufacturing optimized UAV printed in one shot, absolutely bespoke for its environment, ready to fly. All the control systems go in place and it's ready to go. If you need to change the design, if it needs to move somewhere else, redesign it. The programs are already set up, 5 days from start to finish, ready to fly. EADS were particularly happy with this particular prototype. They put it on display at the Farnborough International Air Show. This was in the main stand alongside the A350 presentations, the big A380, and it generated significant public interest, national news headlines. Furthermore, we have had significant success putting some of these concepts and demonstrators into the Science Museum in London, and some of it has even made the international news. So to conclude, these are quite interesting times for commercial aviation. But all of the technology that I've shown you today is the very, very early stages of development. Even more so the tool sets that we're developing right now. Additive manufacturing for large, complex components is still difficult due to the physical properties of the process. Prior manufacturing analysis, as shown in the hinge, can actually significantly contribute to the optimization of the design. We end up with a significant improvement over conventional techniques. Education, industrial links with students and universities is particularly important, which is why I sponsor so many projects at the universities. Educating the next generation of engineers, the next generation of people coming into these industries is of particular importance. We believe that the tools generated as part of this will actually significantly contribute to the next generation of aircraft. That's a nice point to conclude, so thank you for your time. I'll have to take any questions that you might have.